Well, hello students. As we said in the first video, the purpose of this course is to give you an overview of science in our lives and the role of science in society. The intention is not, I stress, is not to convert you to being a scientist, but to enable you to have a greater understanding of how science is done, an understanding of some of the more important discoveries and understandings achieved through science, have a better appreciation of the physical and biological world around you, and to understand the fundamentals of how our bodies work, etc. At the beginning of the accompanying course, Level 150, we talked about how science is done. That is, we talked about measurements and precision and accuracy, the scientific method, which involves making observations, coming up with hypotheses about how some phenomena might work, designing and carrying out tests of our hypotheses, analyzing the results, and modifying our hypotheses if necessary, and then carrying out this process in an iterative way until we achieve an understanding of the phenomenon. And if the phenomenon is very important in nature, this understanding might then be called a capital T theory, like the theory of gravity, or atomic theory, or the Big Bang theory. Or in the semester, we will talk about plate tectonic theory and cell theory. But most scientists will carry out studies throughout their careers and make incremental improvements in our understanding of some phenomenon without having a capital T theory to be put on their resume. Now, advances in scientific understanding are closely aligned with improvements in technology. That is, developments of something new that improves our lives, for example, improvement in modes of transportation, improvements in the efficiency of the generation of electricity, new and better modes of communication, new drugs or medical procedures that help cure diseases or improve our health, ways to produce higher yielding and more nutritious crops, better ways to protect ourselves, whether this be weapons used by the military or new ways to identify criminals via DNA fingerprinting, for example. So science and technology are closely related, with technology often following on the heels of some scientific discovery. Now, how were scientific discoveries, through the research of scientists, done throughout the ages? In the accompanying course, we began by talking about some early astronomers. Remember them? Copernicus, Kepler, Galileo, and others, and how their observations led to our understanding that the Earth revolves around the Sun, that the Earth is not the center of the solar system, but is one of the planets of the solar system. And these discoveries then also led to our understanding of galaxies and the universe. We also then talked about Newton and others who studied the force of gravity and other forces in the field of physics called classical mechanics, which helped us understand the basics of the motion of objects, things like momentum and velocity. Then we talked about scientists who studied steam engines and the phenomena of heat, people like Joule and Clausius and Lord Kelvin and James Watt, and scientists who discovered electromagnetism, Maxwell and Faraday and Volta, and yes, even our own Benjamin Franklin. The point is that science that was done prior to about 1900 was carried out primarily by a few brilliant and brave individuals. Consider Alexander Graham Bell, who developed the telephone, or Thomas Edison, who developed the light bulb, or the Wright brothers, who developed motorized flight. Now, each of these individuals had limited sponsorship, especially very limited, if any, from the federal government. Mostly they were doing their research on their own dime and on their own time. True discoverers. But then World War II happened and things changed dramatically. During World War II, both in the United States and England and Canada and other countries, scientists and engineers became much more important in the development of the tools of war, including the atomic bomb. The Manhattan Project in the United States and what was called the Tube Alloy Project in England and Canada led to our understanding of nuclear fission reactions, unlocking the secrets of the atom, and to the ultimate development of the most powerful weapon, the atomic bomb, which then was used by the U.S. to hasten the end of World War II. Following World War II, science then was very highly regarded in the United States. This led to the creation of such federally funded agencies as the National Science Foundation, NSF, DARPA, the Defense Advanced Research Projects Agency, NASA, the National Aeronautics and Space Administration, the National Institutes of Health, NIH, the Centers for Disease Control, or CDC, the Environmental Protection Agency, etc. We also saw the beginning of the great partnership between the federal government and research laboratories at universities. Presidents from Truman on have had a science advisor, though Nixon fired his, and then Congress then established the Office of Science and Technology in 1976 to reestablish a science advisor. Vannevar Bush, shown in this slide, was the first science director under FDR and Truman, and he was very influential in influencing the federal government to invest in science and engineering through these agencies, particularly the National Science Foundation. You'll notice that many of these federal agencies were created between about 1950 and 1970, and I just give the dates of these because I think it's kind of interesting that it's hard to imagine that we would have the political agreement in Congress to form some of these agencies at this point in time. But during this period of time, there was a consensus that we need to invest federal funds in these agencies that supported developments in science and technology. And then Sputnik happened, this Russian satellite that orbited the Earth in 1957, which then shocked and surprised the leaders in the United States and led us to invest even further through the creation of NASA and DARPA and also the National Defense Education Act, and to then set a goal which ultimately led to landing a man on the moon. And this shows, for those of you who have not seen, if there's anyone who has not seen the photos of the Neil Armstrong first stepping on the moon. One small step for man, one giant leap for mankind. And it was interesting that Neil Armstrong at the time, he also was quoted saying he was probably the only person in the United States who was not watching television at that point. So during this period of time, there was a great investment of federal resources in science and technology, and science and engineering was held in very high regard. Here's a quote from C.P. Snow, a British scientist and novelist, who stated in an article in something called the American Association for Advancement of Sciences in 1960, that scientists are the most important occupational group in the world today. What they do is of passionate concern to the whole of human society. So this is like in 1960 that scientists and engineers were considered the most important occupational group. Also, during this time, science was popularized through magazines. You've probably heard of Scientific American, which is one of the oldest, if not the oldest, continuously published monthly magazine in the United States, and also Popular Science and Discover. These enjoyed very large circulations in the 1960s and 1970s. And on TV, very popular PBS series Cosmos, starring Carl Sagan, the astronomer, cosmologist, astrophysicist, astrobiologist, author, and science popularizer. And shows like Cosmos brought science to the masses. Also, there was Walter Cronkite's Universe, Omni, Discovery, and Science 80. And more recently, a resurrection of the Cosmos series has been aired, starring Neil deGrasse Tyson, and you've probably recognized Dr. Tyson. So the 60s and 70s were essentially the zenith of science and technology in terms of its influence on society. But over time, public support for science has ebbed due to a combination of regulatory pressures by the EPA and other federal agencies, environmental and consumer activism, which some people think has gone a little bit overboard, and there has been a politicization of science. There have been scares such as DDT, LR, thalidomide, fears over nuclear radiation and damage to nuclear power plants, 3 Mile Island, Chernobyl, concern or fears about biological weapons, dirty weapons, depletion of the ozone layer, acid rain, AIDS, and more recently the Ebola virus. There have also been controversies related to advances in biomedicine, that is research on stem cells and cloning. There's been a loss of excitement over NASA space travels as these have become somewhat routine. And there have been questions or concerns over fracking and vaccinations and do they cause autism? Fact check at this point. There is no linkage between vaccination and autism. That's just way blown out of proportion. Also, controversies about genetically modified foods. And I give as an example here the question of red wine, good or bad? An example of many things that we hear about where we hear one side, we hear that, oh, this is good for us, and then we'll hear a story about how it's bad for us. Red wine, good or bad? And also, as science has developed, it has become more and more specialized. And this has made it more and more impenetrable to the common citizen. As we've learned more and more about science, it becomes harder and harder for the average person to understand, even at a minimal level, some of the topics. And there has been a pushback by certain parts of society against science. Let's be honest. For example, the religious right has pressured against teaching evolution and the age of the earth in schools and certain types of biomedical research. Industrial leaders, including those in the oil and automobile industries, have pushed back against federal regulations regarding pollution, for example. On the left, extreme or overzealous environmentalists and animal rights activists have also made it difficult for scientists and have drawn the ire of the public. And so the average citizen is left to wonder, who do I trust? Who do I believe? Consider an example. The snail darter versus the Tennessee Valley Authority. Back in 1978, a law was passed, the Endangered Species Act, and at the same time, the Tennessee Valley Authority was building a dam, one of the rivers in East Tennessee. But lo and behold, there was a small fish, just a couple of inches long, the snail darter, found in one of these rivers. And so there was a case brought all the way to the Supreme Court, the Tennessee Valley Authority versus Hill, that ruled that the building of this dam had to be stopped, even though it was about 90% complete, because the snail darter was on the endangered species list. Now, to most people in the public, this seemed a little bit overboard and some confusion as to what aspects of science are most important. Protecting an endangered species versus the developing of hydroelectric power. The impasse was eventually solved by relocating the snail darter, and then the dam was completed. Yet we all like to consume the products of science. What would we do without? And here's a long list. Motor-powered flight, airplanes. The Model T automobile and all the automobiles since then. Broadcast radio, penicillin, antibiotics, the first electronic computer, kidney transplants, high-yield disease-resistant strains of grain, polio vaccines, heart transplants, the CT scans, the linking of computers to communicate with each other, which is the basis for the internet, discovery of HIV virus as a cause of AIDS, DNA fingerprinting, Prozac as a therapy for depression. And just in the last 10 years, the Human Genome Project, hybrid cars. How many of you have a hybrid car? You'll have a hybrid car before long. YouTube, iPhone, and the iPad. So these are some of the things that have been products of science and technology. So these are some of the products of science and technology which we, no doubt, cannot do without. But yet over time, in the last 20 or 30 years, there has been a split between science and government. The snail darter versus the TVA authority is one example. Another example is the following. President Reagan proposed something called the Strategic Defense Initiative Project, which is also called Star Wars, SDI, which proposed that there would be a network of satellites orbiting the Earth equipped with X-ray lasers that would then shoot down any missiles that were launched towards the United States. A grand idea. Now, the scientists who examined the plan concluded that it was essentially bunk. Letter to the president from the Union of Concerned Scientists that said that the X-ray laser offers no prospect of being a useful component in a system for ballistic missile defense. Yet, billions of dollars were then invested in the Strategic Defense Initiative. And at about the same time, there was another conflict between the scientific community and the federal government. That is, a group of scientists wanted to develop what is called a superconducting supercollider. That is, a large racetrack, an atom smasher, proposed to be built in Texas, south of Dallas. You can see the map. They proposed to build a large superconducting supercollider of a circumference of about 40 or 50 miles. And about $2 billion had already been invested and construction was underway. And then the Congress essentially canceled the construction about halfway through. So the point is that science and technology, which had once been so important to society and to the federal government, now was being squeezed out with budget cuts. But yet, progress was still being made in science and technology in other areas, and one was the development of the internet, where we can now get information at a keystroke. Now, this information is usually unfiltered. It's not necessarily placed in context. It may be misinterpreted by those who have an agenda. There are a lot of science blogs that can be more about entertainment than actual explaining scientific concepts. And over the years, there have been a group of scientists who have attempted to champion science and to be science communicators. And I show a set of these. Stephen Hawking, Stephen Jay Gould, one of my favorite authors, Richard Feynman, E.O. Wilson, and of course Carl Sagan. And more recently, we have Bill Nye, the science guy, and Neil deGrasse Tyson. And I show in this slide in the upper left in black and white an image of Don Herbert called Mr. Wizard, who had a TV show between 1951 and 1965, and I remember spending a lot of Saturday mornings watching Mr. Wizard. It was either that or Popeye. Now, these individuals have attempted over the last several decades to make science more relatable to a broader audience. They have tried to counter the trend of science becoming more and more specialized and impenetrable to the public by making it understandable, explaining it in various ways. Has this been effective? It's hard to say, of course. The public wants to be consumers of science and technology, which is perfectly fine. And the public oftentimes sees we scientists as being a little bit on the nerdy side. Okay. So even though we may be considered a little bit nerdy, it is the contention of many of we scientists that all members of society, that is you, can benefit by having some fundamental understanding of scientific principles in order to be a better consumer and to be a more informed citizen. In the next video lesson, we will compare the worldview of science versus other sectors of society. We will now pause for a quiz in which you will be asked a few questions over the material we've covered before you can view the next video lesson. See you then.